Hello. Uh, Today we are going to be solving question 2.1 from the heat and mass transfer 8th edition. This is going to be problems all on Fourier's law within the introduction to conduction section. So for our problem statement, it says we are assuming steady state one-dimensional conduction in the axisymmetric object below, which is insulated around its perimeter. It says if the properties remain constant and no internal heat generation occurs, we must sketch the heat flux distribution Q x double prime and the temperature distribution Tx. We must explain the shapes of our curve and then how our curves depend on the thermal conductivity of the material. So from here on my work done, I had given I've written down the given, which is just a summary of what they gave us in the problem. And then I wrote down the find, which is the heat flux distribution, the temperature distribution, and explaining our curves. So from here is the schematic again, as given here. Pretty similar. I'm a pretty good artist. And then our assumptions. So most of these are from the statement from the textbook. It says steady state. We know that's 1D conduction. So in the X direction, there's no heat generation term, and it's an insulated perimeter, so we don't need to worry about convection. And then also it's axisymmetric constant properties. So everything that is done up here is going to be the same down here. And the properties stay the same. So initially what we could do is we start from our energy balance. So we have energy stored is equal to energy in minus the energy out plus the energy generated. We know that it's steady state, so there's no stored energy. And then we also know that there's no heat generation, so generation is canceled out. So then we have E in is equal to E out, which is basically equivalent to our heat our heat rate is equal to the heat rate plus the change in X, where we know that heat rate is also equal to our heat flux times the area of the surface area that we're entering. So from here we could solve for heat flux, which is one of the things that we need. So it's equal to Qx over AC. So as we could see, when the area increases, our heat flux decreases. So they are inversely proportionate, like I mentioned, or like I written down here. So that's that quick little explanation. So as we increase with X, you can see that the heat flux decreases due to that thicker geometry towards the center. And then it increases back up to its original statement or original value. And then for temperature, we know that heat flux is also equal to negative K times dt over dx. So negative K are thermal conductivity, and then dt over dx is just the derivative of our temperature function by x. So from here, our heat flux, as it decreases here, the temperature is going to decrease, but we also know that T1 is greater than T2, so it's pretty obvious that the temperature will continuously decrease over length. So as L gets larger, we can see that it's inversely proportionate to the heat flux. So from here, I wrote that the slower temperature drop is due to a lower heat flux. As we could see, it kind of almost flattens out when the heat flux is super low. And that's pretty prevalent from the equation here. And then finally, how does your curve depend on the thermal conductivity of the material? Well, it's pretty obvious here that the thermal conductivity is given in this equation, changing the temperature, or it's associated with the change of temperature over the change of X in our heat flux here. So really simple question for work, but it's very theoretical. I do hope this helped. Um, I know this didn't take too long. Refer to your textbook if you have any questions. It gives you some of the equations like over here that I'm showing you. Here's the two equations that I used where heat flux is equal to the heat rate over area. Um, and then it's also equal to the negative K dt over dx to solve for that temperature change. So yeah, thank you. I hope you enjoy this question.